radius ratio and stability of ionic crystal. Okay, radius ratio and stability of ionic crystals. Okay, the stability of ionic crystal can be determined with the help of radius ratio values. For this, an ionic compound of type AX is considered the coordination number of A positive ion in this compound is 3. 3x ions are in contact with one anion. This has been shown. You can show this figure. A positive ion, X negative ion, X negative ion, X negative ion. This is R positive upon R negative is greater than 0.155 stable structure. Okay. This structure is very stable. This structure is very stable. This structure is very stable for the stable arrangement of crystals. This structure is very stable. This structure is very stable for the stable arrangement of crystals. For the very stable arrangement of crystals. First point. The cation must be in touch with all the anions. The cation must be in touch with all the anions. As the cation A positive is in contact with three negative ions. X negative. Our forces of attraction will be more. Ions, the forces of attraction, the forces of attraction will be more. Okay? Will be more. Second point. As the anions are not in contact with each other, the forces of repulsion will be useless. As the anions are not in contact, with each other, the forces of repulsion will be quite less, quite less. Okay, the process of repulsion will be quite less. If the negative ions, if the negative ions are in contact with each other, which is shown in figure, you can show this is positive ion, and this is positive ion, and this is X, negative ion, this is X, negative ion, this is X, negative ion. Okay, this is figure number B, and R positive upon R negative is equal to 0.155, limiting case of stable structure. This is limiting case of stable structure. Okay, this is limiting case of stable structure. If the negative ions are in contact with each other, if the negative ions are in contact with each other, you can show this figure. This is the limiting case of stability of coordination number 3. This is the limitation of the case of stability of the case of coordination number 3. Okay? If the negative ions are in contact with each other, which is shown. This is the limiting case of stability. This is the limiting case of stability. This is the limiting case of stability of coordination number 3 of coordination number 3. In this case, cation is steel. Cation is steel touching the anion. Steel touching the anion. Here the force of attraction is strong. Here the force of attraction is strong. Okay? As the anion are also touching one another, thus the force of repulsion will be stronger than V4. As the anion are also touching one another, thus the force of repulsion will be stronger. The force of attraction will be stronger than V4. Okay? By the simple geometry, this given the radius of R positive ion upon R negative ion is equal to 0.155. This is the lower limit of Cn number 3. This is the lower limit of coordination number 3. This is the lower limit. This is the R positive ion upon R negative n equal to 0.155 is lower limit of coordination number. Okay? 3. Coordination number equal to 3. If the radius is less than 0.155, then the cation is not in contact with anions, and the structure is also, you can see this figure. Figure number 3. You can show this figure. X negative ion, X negative ion, X negative ion, and this is positive. Okay? Then if the radius ratio is less than 0.155, if the radius ratio less than radius ratio, if the radius ratio is less than 0.155, ratio is less than 0.155, then the cation is not in contact. Then the cation is not in contact, with anions, and the structure is, you can show, the structure is unstable due to following reasons. Okay? The structure is unstable. The structure is unstable. Okay? The structure is unstable. Okay? And next, two anions are in direct contact with one another. Two anions are in contact with one another, hence the force of repulsion will be quite more, and the force of attraction, hence the force of attraction, the two anions are direct contact with one another, hence the force of repulsion, and the force of repulsion will be quite more. Okay? Second point. Since the cation is not in direct contact with anions, then the force of attraction will be quite less. Since the two anions are in direct contact with one another, hence the force of repulsion will be quite more. And since the cation is not in direct contact with anions, hence the force of attraction will be quite less. Thus, from the above discussion, it is clear that if the value of radius ratio lower below 0.155, for coordination number 3, the structure will be unstable. Thus, the limiting radius ratio for coordination number 3 is 0.155. For each coordination number and geometry of the ionic crystal, the value of radius ratio is calculated if the ionic radii are known. This radius ratio is called as the limiting radius ratio. If the value of radius ratio falls below the limiting radius ratio, then the ionic structure is unstable. Okay? As the difference in the size of the two ions increases, as the difference in the size of the two ions increases, the radius ratio also increases. As the difference in size of the two ions increases, the radius ratio increases, and at some point 0.252 to 5, it becomes possible to fit 4 ions around one, and so on 6 ions around one, and 8 ions around one, and finally 12 ions around one, due to which coordination number 4, 6, 8 and 12 occurs. Thus, as the cations becomes larger with respect to the anions, the coordination number of cations increases. Okay? The coordination number of cations increases. As the cation becomes larger with respect to the anion, the coordination number of cations increases. Okay? Thank you. Studying the principal moments. Studying principal moments.